the chamber. Movable shield. So this is, I already told, this is actually one shutter. So during deposition, when you feel that actually the deposition is sufficient, or is kind of stable deposition is happening, then only you can open the shutter. So if you open the shutter, directly it will be deposited on the sample or your substrate. Okay, and this is the material for deposition. So here, by using resistive heating, that different like material will be placed here. And this is the chamber wall. This is the chamber wall, and this is actually one crystal sensor. So this crystal sensor actually indirectly it will deposit there itself, and it will tell how much is that deposition rate or how much is that thickness, deposition thickness. Okay, rate and thickness it will tell this sensor. And there is a pressure sensor here, another one. This is very much important because whatever the inside pressure, that is actually where you need to know continuous monitoring is required. And there are two pumps is attached to that physical vapor deposition. One called RAP pump, another is called turbomolecular pump. So when I will talk about the pump, there actually I will discuss, but you keep in your mind at the beginning. So first what happened, that you need to place your sample here, then whatever material you want to deposit. So if you want to deposit gold, so gold needed to be placed here. Then you close the chamber. Okay, close the chamber, and this inlet valve you close it. And now you start that roughing pump. So roughing pump actually what that will do, it will actually give you some pressure like 10 to the power -2 to -3 millibar. It will give the pressure. Okay. And then if you reach that pressure, then you have to start high-end pump, that is called turbomolecular pump or sometimes diffusion pump. So this turbomolecular pump at the beginning you should not start. When you have to make sure that you achieve some sort of vacuum, then only you need to start the turbomolecular pump. Then turbomolecular pump, if you start it, then you can reach up to 10 to the -6, 10 to the -7 millibar pressure. And there is this outlet is there. This continuous actually molecule will come out through this outlet. So whatever the molecules are there, gas molecule, air molecule, it will continuously, it will be coming out through this pumping action. Okay, so this turbomolecular pump, then, so if we reach, let's say that we achieve 10 to the power -6 that vacuum, so then only that we'll start it. Now let's try to understand that how is that this process is happening. Right. Then if we achieve the vacuum, then first we need to heat the substrate, then deposition will start. And when if you get that through this crystal monitoring, you can monitor how much is the deposition, and when you feel the deposition is stable, then you open the shutter and allow to deposit on your sample, and you can monitor rate, deposition rate as well as the thickness both on your sample, effective thickness. And then when you feel that, okay, let's say you want to deposit 100 nanometer, 100 nanometer is over, first job is there, close the shutter. Then here slowly you reduce the voltage. If you reduce the voltage, what will happen, that here temperature will down, and so that evaporation will be less. And but first you have to make sure that this is closed. So then what happened, that this voltage slowly it will come down to 0, and this one temperature will actually come down slowly. And when this temperature will come down, then what will happen, and this two pump is also running. So first you need to close the turbomolecular pump, and then what happened, that if you close the turbomolecular pump, then this pump actually always will be running, because this pump will be continuously running, and then this will be closed first, and then it will be running, and slowly this will be also, you have to close, and then you need to purge the gas inside, and then you can open the chamber and you can take your deposited film. So let's try understand that mechanisms. In most cases, the source material is heated from a solid state to a liquid before vapor. Okay, this is the source material. Now actually in that this schematic cartoon we will be watching this this what is happening here. And in between, if you have any question, please stop me and ask the question. Okay. But this operation actually, please understand. So material for deposition. So this is actually first step. So therefore, source material is supported from the beneath. So at the beneath, the source material and there is a resistive heating arrangement will be there. Okay, resistive heating arrangement will be there. So you can see, then this is the samples. You have to make sure the sample in the proper place, and this is actually already done. So you put it. So vaporized source material rise upward towards a downward facing target sample. So downward facing target sample is here. Then this quartz crystal sensor enable control of the source material vaporization rate. So this is the quartz, crystal sensor. So that is actually will tell you how much is the deposition. So this is actually when I talk about the vacuum. So there actually that I'll talk about the DTM crystal also there. Now this movable shield, so this rate control is coupled with a movable shield to allow the specific thickness deposition on the sample. So let's say that when you feel that deposition rate is fixed or you have maintained, then you can open the shield and you can, in the sensor, you can make it 0, and then that it will be directly deposited on the sample, because on the sample deposition rate as well as thickness both you need to know. So then actually evacuation of the chamber gases is required before the source material can be deposited on the sample. So first actually you place this sample, and this you make sure that actually that DTM crystal that is also there. So then this is this, yeah. So this is first a wrap pump. So just actually previous, I'm sorry, actually this is what happened, that in the chamber is open condition and here the material is placed and this is sample is placed here, DTM also is here. So just actually all the parts is there. Now this, I just little bit make it fast. So that evacuation of the chamber gas is required before the source material can be deposited onto the sample. So that is actually happening. I think in the all the operations are there. Yeah. So this is actually the real chamber. This is inside. Just actually first you place the sample. Place the source material. Sample is here. Target yours wherever you want to the deposit. Then what happened, that you close the chamber and this inlet valve you close it. So inside will be gas from air. So air will be inside. Now actually first a wrap pump reduces pressure inside the chamber to around 10 to the power minus 2 Pascal. So this roughing pump, that is actually you can see this air molecule, it's sucking the air molecule and actually removing from the chamber. So then this is turbomolecular pump reduces pressure inside the chamber to 10 to the power minus 2. So initially it was around 10 to the power 2 Pascal. That time you start the roughing pump, then 10 to the power minus 2 when it's less than 10 to the power minus 2 Pascal. So you can start this turbomolecular pump. So this absorbed molecule can be the suborn to remove. So this is actually this turbomolecular pump actually is removing this whatever this gas molecule, and mean free path will increase inside the chamber. Now that heating operation, so registered heating, resistive heating vaporizes the source material. So once you got the high vacuum, then resistive heating will start, and then immediately that evaporation will start. But when evaporation starts, you can see that this it can't deposit on the substrate because you have a shutter. So shutter is closed, but it can go to this DTM monitor. So this crystal quartz crystal monitoring system. So quartz crystal monitoring can tell that how much is that rate of evaporation. And this operation turbomolecular pump will be running. Now this quartz sensor is used to set that vaporization rate. So once actually that you finalize, okay, this rate I want from this quartz sensor, then you can open this shutter. So you can see that here that now the shutter actually removed, and then now the deposition on the substrate. So then resistive heating vaporizes the source material onto the sample. Now actually it's on the sample, and DTM crystal will tell how much is the deposition rate and what is the thickness. And turbomolecular pump will be running in this condition. Next is the vaporized source material impinge on the surface, substrate surface where it settles and condense. So that as I told the mechanism of the physical vapor deposition, so according to that action, that film will form. Condensation will form. Because condensation will accelerate the film formation. So once a film of the desired thickness is obtained, the shield is returned to cover the sample and resistive heating slowly ceased. So first job, you have to close the shutter, and then slowly you have to reduce that applied voltage because they are actually resistive heating. So I square RT, and this one slowly you have to come down, make it down. So now this result in a film on the source surface covering that sample surface. So source material, the source material will cover the sample surface. That is actually basically nothing but a film. So that is you can obtain by physical vapor deposition. Okay, so this is that the video. So any questions from this video you can ask. Otherwise, that I can start the next section. Any question?
Is there any partition between the shutter and the quad sensor?
Any? Is there any?
Like
Louder?
partition between the quad sensor
No,
and the substrate?
no. Actually, that this is actually ideally this should this quad sensor actually this shutter actually will not make any obstacle to the quad sensor. Okay, it will be in such a position that if you close also, that you can observe clearly the deposition.
So won't some of the vapor go to the substrate as well then if there is no partition between quad sensor and the substrate?
No. Actually,
even with the shutter.
yes, purpose. What is the purpose of the shutter? Purpose of the shutter, I want a control deposition and I want a specific thickness, right? Specified thickness. So I want 100 nanometer thickness. So 100 nanometer thickness. So in this case, what is happening? So yeah. So first, actually, what happened that initially, if you start, the deposition rate will be very slow. Then with increasing the voltage, deposition rate will increase. Okay. Then when I feel that okay, some sort of deposition rate, let's say that I want, let's say that 10 nanometer per second. Okay. So 10 nanometer, it is a bit high. So let's say that 5 nanometer per second. So 5 nanometer per second or 1 nanometer per second, let's assume. So that is actually I achieved. Then I'll open this shutter. Because if I close the shutter, because this shutter will be very close to the substrate, so it's on the substrate there will be a no deposition, but this atom, evaporatory atom, continuously will come to that crystal, monitoring crystal sensor. So purpose of the shutter is to close your substrate wherever you are depositing. So when you make sure that your deposition rate is fixed, then only you should open that shutter. Is it clear? Is it clear? Is it clear?
Sir, still want the vapor, like vapor has the tendency to fill all the space which is present.
Yeah,
So want some of the
that's
substrate.
true. That's true.
So
Because
want
that,
some of the so so that's what I'm asking. Like
yeah, yeah,
when it reaches the quad sensor, some of the vapor might also get deposited on the substrate as well
yeah. But this is
during that.
actually, this is a schematic cartoon. So this substrate will be very small size compared to the shutter. Okay. So this is actually schematic. So here the big substrate is there. So ideally substrate will not be such a big. Substrate will be very small. Okay, in PVD. So when you will have a big shutter, so definitely actually below the shutters that there will be a no deposition. But this in this cartoon that you can see that this is actually basically that in the cartoon also, because this is like but deposition will be there on your DTM crystal, because DTM crystal you can see the straight line also it may come there. Okay, but this is entire top is not a substrate. This is a substrate holder. So here at the center you have to place your substrate, small substrate, but substrate size is much smaller than shutter size. Now it's clear.
Yes, sir.
Okay, any other question? Please do ask. I shall be happy to answer your question. Okay, I'll move to the next slide. So there also, if you have the question, you can ask it. So in physical vapor deposition, so this is actually the same schematic cartoon. So this actually in this picture it will be clear. So substrate will be here, and here the shutter will be just below the substrate, and it can be operated from the top only. Okay, so then and let's say shutter will be like this. So if this whatever that flux is coming, that is actually without any hindrance, it will come to the monitoring, digital monitoring, thickness monitoring. Okay, the sensor it will come. This substrate, sorry, shutter will not be a hindrance for this sensor. But when you, let's say that you want 1 nanometer per second, so you start it here, initially it will be very low, initially maybe 0.1, then 0.2, slowly rate will increase, 0.3, like that, and finally you reach that 1 nanometer per second rate. Shutter is closed up to that. Then what happened that you make it like zero, you make it zero, the DTM crystal. So DTM crystal will continuously tell the thickness because it's coming here. Okay, it will tell thickness whatever accordingly, but you make it the thickness zero, but you know that what is the deposition rate and you open the shutter. Then what happened that 0.1 nanometer per second, that is actually atom is coming, I mean deposition rate, so that is actually deposition rate. and thickness also it will tell. So when it will reach 100 nanometer, because you make it 0, this one zero balance, like if you take a like zero balance we used to do for taking balance of like any weight measurement. Similar here also you can do the zero balance. So 0 you make it, then 100 nanometer it will be there. When it will reach the 100 nanometer and you are keeping fixed the deposition rate 1 nanometer per second, the 100 nanometer thickness is over. First job will be there, close the shutter. Then here actually you slowly reduce this chamber. Immediately you should not here that reduce that voltage. If you voltage, then here it will break. Okay, this resistive heating. So slowly you need to reduce the heater temperature. But shutter immediately should be closed. Is it okay? Yeah. So this is actually how that board is looks like. This is actually board, tungsten board, and here that this is a gold deposition. So you can see the gold ball is placed here, and this board is fixed with the screw, and these two, that this is a copper wire. This copper actually is the electrode, nothing but the electrode. So this is that like tungsten has actually resistance is high. So in with actually resistive heating actually it can here the temperature will generate I square RT and this will melt. So this is actually how this sources looks like in physical vapor deposition, and this is called boat. This is again another one picture of the boat. So this first actually this boat, if some screw is there, one screw and this screw, you have to remove the screw, and then this boat you have to fix it first, and you have to tighten this one. This is your electrode, and then you have to place the source material here. This is you can see that source material, and this is the shutter. So it's very close this one, and sometimes actually it can be close to the source material, and sometimes actually it could be very close to that substrate. So substrate will be here. This is actually substrate will be just here nearby, and this is actually you can see the source, and this is the shutter, and here just above the substrate your source will be coming. This is again like some material like aluminium. The boat is not required, their coil is required. So in this coil, tungsten coil, that aluminium will be in tungsten sometimes. This case tungsten last class I talked about. So but molybdenum also can be used sometimes. So this is actually tungsten filament. So in this filament that you need to place that small pieces of the coil, and this will melt. And then what will happen, that melt actually will wet the entire coil first. Then from there aluminium will evaporate. So how the sources looks like. This is you can see that 3 sources there, 3 electrode arrangement, and this is the shutter. And above the shutter your substrate will be there. Okay. So this is actually 1, 2, 3. And every actually board. This is board, you can remove it using this both screw. And so this is one and 2. This is one electrode setup. This is another one setup. This is third setup. So anode cathode, here anode cathode. Like 2 terminal, not anode cathode, 2 terminal. This is actually you can see here again that this is that here source is there, and just above the source in this case the shutter is there, so that actually you have to contamination, the chamber contamination will be very less. But in this case actually I mean problem is that actually the digital thickness monitoring like actually you have to fix in some nearby distance. Okay, so if you have this kind of arrangement, so but this distance actually movable, you can adjust the shutter position. So this is actually you can make it up wherever you want, you can make it. So this is actually it's here means it's not like that it will be here only. So movable, you can, let's say you can fix it in this position, so that actually it will not act as a hindrance for this digital thickness monitoring. Again, this is that 1, 2, 3. So 3, this one left side one coil, right side one coil, and the middle one board is there. So that 3 I mean metal heating arrangement is there, and this is actually that shutter, and above the shutter this is that your substrate holder. Okay, and this entire that chamber will be covered with another one setup there, like that. Again, this is that you can see that this is a shutter. So how that you can move the shutter? Okay, this is a shutter, and this shutter actually can be moved. And this is the board. So this is actually one schematic of this like PVD chamber. You can see that this is actually sometimes made of glass. So here this is that like whatever that, as I told, that bottom is that vacuum chamber, because that you need that two vacuum. One is roughing vacuum, another is actually turbomolecular pump kind of high vacuum arrangement is required. And in this chamber there are one is a resistive heating where source will be there, then shutter, substrate, and one digital thickness monitoring, and one pressure gauge. So this is actually like PVD chamber, and this is inside that how the source. This is like actually one two screw, and this is actually movable. That board, in that board, whatever material you want to deposit, you have to keep it. And here you can see that this is that arrangement of the board. So whatever board it will be arranged, and this is thickness monitoring, and this is the shutter here, and this is the substrate holder. So this shutter will end here, and this is the thickness monitoring. So it will not at all any hindrance to this thickness monitoring. Okay, so this is like one schematic of this physical vapor deposition. So this physical vapor deposition, you have to some actually that impression will need to be built in your mind. Actually, generally every year what I used to do in our department, we have a PPT chamber. So in this class, the student I used to show a demonstration, but now that is not possible. So that's why actually I'm showing the picture. Actually, how this PVD chamber is looks like. This is that, I mean, the chamber, and this is here the gauge are there. So the gauge, one gauge will tell inside pressure, another actually DTM also that will be connected here. So here this is actually DTM monitoring. So there are two gauge. One is actually low vacuum gauge, another is high vacuum gauge. This is the digital thickness monitoring. So digital thickness, so low vacuum. First you have to make sure that you reach 10 to the minus 2 Pascal or millibar. Then only you need to start high vacuum, and then 10 to the minus 6 or minus 7 when it's reached. Then you need to start the operation first with the increasing the voltage. So here the option will be there to increase the voltage of the source, and then actually deposition will start. And from this thickness monitoring, immediately you will be knowing that when deposition will start. It will tell, because when the deposition will start, atom will go and impinge on the DTM crystal, and this DTM, now question is that DTM crystal will be fully deposited. How it works? DTM crystal will be a vibrating, it's a piezoelectric material, so it will vibrate, it will oscillate. Okay, so there actually as such much deposition will not be there, but through the knocking it can tell that how much is that atoms are coming. So then DTM will tell that your deposition is started or not. So when you saw that, okay, here some reading comes means deposition starts, because by this chamber hole, it's you can't see the deposition started or not. Only you can see that your boat is red hot, and so let's say the gold is melt. That's all. But deposition will tell this one. So that's why in digital thickness monitoring is very important. So I mean, if it give the wrong data, you may have the wrong deposition. Like you want, let's say that 100 nanometer, but you deposited, let's say, only 20 or 30 nanometer. This is give you wrong information. So that's why actually time to time that this is actually it's need to be calibrated properly. So this is a common problem in thin film deposition, that you deposited, and then by using some profilometry, when you check the thickness, you are getting the lower thickness whatever DTM is showing, or sometimes higher thickness whatever DTM is showing. So in both cases can be rectified. And this is actually in this case that vacuum, like actually which vacuum I want to start, that is actually can be started. Okay, and the chamber also opening and closing. So I think this is actually the one vent is there, that is actually at the end of the operation when you want to open the chamber. So this vent will be open so that air will purge inside, and then you can take out your substrate. I mean this your deposition. So with that one, just actually I want to finish that today's class. And if you have any questions, please do ask. Please to ask any question to us, because I want you should be. It's a clear that chamber. Tomorrow, if you see any vacuum chamber like PVD chamber, you should know what is inside. You should know what is inside. And this PPT I am not going to put in that Moodle, because this is actually very simple PPT. So because already I put some of that I put it, but if you want, then I can put it there. For me, no problem, because already all the picture reference is there, so no problem. And also that I just like to ask one thing. One student I found actually, so I just one student in that project I found that he's alone. So what can be done? So maybe Utsav, you please tell some suitable solution later on. Okay.
So I guess there are odd number of students, so one student has to be alone.
Okay, so then if he actually not comfortable alone, then maybe one group with 3 students have to make. Okay, but if you want to do alone, I don't mind. So please convey this
Okay.
message. But thing
I
is
will
that
just
it should
tag
not be a
him.
compulsion. Like actually no group want to take him. In that case, actually he has to do alone. Okay. That student name is Pradeep. So
Yeah,
please,
sir.
Okay.
Pradeep is here.
Yeah, sir.
Yeah. So Pradeep, what you will do? Please actually let me know. So please actually you can do alone. This is option number 1. Option number 2, actually you can join with the group. Most probably tonight or tomorrow I'll give the topic. So before that I want to settle this matter. You want to do alone, Pradeep?
Alone. No, sir. Alone.
It's not a problem. I mean, sometimes alone doing better, because yeah, you can whatever you can download and you can make your report. Okay, but if you want to attach with some group, option number 2, other group also should be agreed. Later on, those groups should not tell no, sir. Actually, you unnecessary make a compromise of these 2 groups. It's not like that.
Yeah, I think I'm alone, sir. I will.
Okay, then it's great. Okay, that's okay.
Okay, thanks.
Don't be afraid. Take a challenge. Take a challenge. Now you're final year, so you should not be afraid. Okay. Okay, then actually, then I'll total number of topic. Then it will be 14 topic. Okay. So 14 topic. Then soon actually I'll send to you, and also that in Moodle also I'll put it. And up to yesterday's class, or I put it that all the PPT there itself. And today's class PPT I think you don't need, right?
But sir, please upload on the RS. Yeah, it gives some ideas.
Okay, fine. So I'll just take the attendance and then let's wrap.
Okay, sir.
Please don't leave. Let me download this file.